All right, let's hit week 5, lecture 1, logistic regression analysis. So you use logistic regression analysis when you want to assess the relationships between one dichotomous outcome variable, so that's like your DV, and one or more predictor variables. That would be your IVs or independent variables. So the cool thing about logistic is that your IVs or your predictors can be continuous. They can be like interval and ratio data. They can be ordinal, but they can also be nominal with any number of categories. So hopefully when you see the description here up top of one to use, you see that this is kind of like linear regression because it kind of is. You're predicting something, right? Or assessing the relationship between some DV and some independent variables. But the difference here is the outcome variable is two-level, dichotomous variable, dead, alive, um, completed therapy, didn't complete therapy, that sort of thing. And the predictors can be pretty much anything under the sun, which is what makes it cool. So it is similar to linear regression, except the DV is dichotomous, and there are fewer statistical assumptions. And it's particularly useful if you want to use it kind of like ANCOVA. So you want to remove the effects of some potentially confounding variables that could bias or obscure a relationship between some primary independent variable in the DV. So you want to adjust for a couple things first and then see is there a difference in the DV associated with this primary and most important independent variable. So number one. Do DUI offenders who attend Alcoholics Anonymous versus Rational Recovery differ in their DUI recidivism? So DUI recidivism means getting another DUI, for those who don't know. And so when judges send them to Alcoholics Anonymous versus Rational Recovery, is there a difference in their subsequent DUI rates? So your dependent variable here is DUI recidivism. 0 is did not recidivate, and 1 is they did recidivate, so they had another DUI. Independent variable, here there's just 1, is the type of program. 0 is Rational Recovery, and 1 is Alcoholics Anonymous. How about, do California drivers with licenses to drive commercial vehicles have a higher odds of crashing in a 1-year period than those with non-commercial licenses? So that is, do big rig truck drivers and whatnot, bus drivers, those are commercial drivers, do they have higher odds of crashing within a 1-year period than non-commercial drivers like most of us? DV here is crash status, something like that. 0 is didn't crash, 1 is crashed. Independent variable is a type of license. 0 is a non-commercial license, and 1 is a commercial license. How about a third one? So those ones kind of seem like you can do with linear regression. So how about this? Is body mass index, that is BMI, related to your chances of crashing or getting a traffic violation during your first year of licensure? So your dependent variable is crashed 0, or excuse me, did not crash 0, crashed 1. Your dependent variable 2 is whether you got a ticket or not. 0, you didn't get a ticket, 1, you got a ticket. So there's 2 different DVs here. This would be 2 separate logistic regressions. Your independent variable, though, is something a little different. It's 0 for normal weight, 1 for underweight, 2 for overweight, 3 for obese. And so notice that BMI is an ordinal variable, but here I've coded it as nominal with 4 levels. I've made 0 normal weight, then 1, 2, and 3, the non-normal weights as other categories, 1, 2, and 3. So 0 is normal weight, so all the other weights are going to be compared to the normal weight when the logistic regression analysis is run. So nominal variables can be used as predictors in logistic regression when you do what's called dummy coding. And I'm going to show you how to do dummy coding. That's the real term. In case you're wondering if I made that up. That's the real term for this kind of coding. So why not just use multiple linear regression, right? You already learned that. Why not just use that instead of logistic regression and predict your 2-level outcome? Well, a couple reasons, of course. When your DV is dichotomous, you should not use multiple regression analysis because, 1, linear regression doesn't just predict 2 outcomes, a 0 or a 1, like whether they crashed or not, or survived or not, and completed the survey or not. it gives you all continuous values in between, and sometimes even less than, like negatives and stuff. So let's say your dependent variable thing you're predicting is sex, where 0 is female and 1 is male. Linear regression model will predict for cases in your data file all sorts of other things besides 0 and 1. It'll 0.45, negative 1s, 1.25. What do those mean? Only 0 and 1 have meaning for a two-level variable like this. And so linear regression gives you junk predictions, I guess is the simple way to say this, because it gives you continuous predictions. You want to know, are they 0 or are they 1 only? You will also violate the normality in homoscedasticity statistical assumptions. Prediction errors for dichotomous DVs aren't normally distributed or homoscedastic. It's got to trust me on that one. So anyway, another reason it violates the assumptions. And finally, and importantly, is logistic regression handles nonlinear relationships between IVs and DVs, and linear regression, it's in the name, right? Linear regression does not, okay? So it does not do a good job of handling nonlinear relationships between IVs and DVs. Logistic allows for the relationships to not just be straight line relationships between the IVs and DVs. They can be curvilinear and all sorts of craziness. So it's important that you code the outcome variable, that is your DV thing you're predicting, in a particular way with logistic regression analysis. It's got to be nominal and it's got to be dichotomous, but it should be coded like this. 0 is the event of interest did not occur. So you use 0 to mean, yeah, the outcome I'm interested in studying here did not occur. 1, the event of interest did occur. So for each person, they get a 0 or 1 on the DV, and it's 1 if the event of interest did occur. So they successfully completed therapy, or they recidivated, or whatever it is you're interested in actually studying, that's coded 1. And 0 means it did not happen. So 0 is lived, 1 is died. So interestingly, logistic regression, unlike linear regression, does not directly predict the DV. It doesn't say, you know, you're a 0, you're a 1 directly. It predicts the odds of being in the category that's coded as 1. So that's why it's important that 1 be used for the category of interest, because it says, I think there's a 75% odds that this person is in category 1, and it therefore you set a rule, like if it's higher than 50%, put them in category 1. If it's lower than 50%, say they're not in category 1. So the odds of dying, for example, would be the odds of being in category coded as 1. So for your independent variables and your covariates, so again, they can be any scale of measurement you want, any number of levels of nominal variables. Usually there's one of your independent variables that you're most interested in, right, for testing some sort of hypothesis or relationship. And the others are covariates. You just want to adjust for, you know, differences between the groups on a couple variables, then see if they differ on the one that's of most interest. So your continuous and ordinal independent variables or covariates can be entered right in the model. Just pop them right in, just like with linear regression. However, ones that are categorical, so they're, whether it's 2-level nominal or 3-level nominal or X-level nominal, you need to code what are called dummy variables, where you have number of dummy variables -1, or it's k-1 dummy variables for a particular variable. So if you have 2 levels, number of levels -1 is 1, you need 1 dummy variable. For a 4-level, say BMI, you would need 3 dummy variables. So it's k-1 levels. So the cool part is SPSS just does this for you. You just pick, hey, do I want the first group or the last group to be the one that the others are compared to? So the level of the nominal variable that is not represented by the dummy variables, because if you think about it, there isn't a level for each single, or dummy variable for each level of the independent variable. There's one that's left out, and we call that the referent level. That is the level to which all the others are compared. So like with BMI, if we coded dummy variables for underweight, overweight, and obese, the one that's left out is normal weight, and all the others would be compared relative to normal weight persons. So let's do an example of BMI with 4 levels, dummy coding. So here we have 1, 2, 3 0, 1, 2, 3, so it's actually 4 levels of BMI. And SPSS has created BMI Dummy 1, BMI Dummy 2, and BMI Dummy 3. So BMI Dummy 1 here is all zeros except for a 1 on underweight. That means the people who are underweight are coded as 1 on BMI Dummy 1. So that is the level that is represented by BMI Dummy Variable 1 is underweight persons. BMI Dummy 2, everyone's coded as 0 except for those who are overweight. So they have a BMI of overweight, they're a 1 on BMI Dummy 2, and so that variable represents overweight. Similarly, for Dummy 3 that SPSS makes, that's obese folks, they're the ones coded 1 on that. So 3 dummy indicator variables can adequately represent a 4-level nominal variable. Again, it's k minus 1, or number of actual levels minus 1 is how many dummies you need. The excluded level is called the referent level, and it's implicitly represented by being 0 across all the dummies. See? So normal weight, note, is the only level of BMI that's 0 across all the dummies. So that means it is the referent. And referent means all the other ones that have a 1 on a dummy will be compared to that. It's like the comparison level relative to this level, relative to normal weight. So we'll get the odds of, say, being in a crash for underweight people versus normal weight, for overweight people versus normal weight, for obese people versus normal weight. So SPSS creates them and enters them, and again, all you gotta do is say, do I want the first level or the lowest level, highest level to be my referent level? And again, the way these are interpreted, it's a little bit different than anything you've run into before. It's the dummy variables are interpreted in relation to how each level compares to the excluded level, in this case, normal weight. So again, overweight versus normal, underweight versus normal, and obese versus normal. So the goals of logistic regression are the same as linear. You want to predict things. You want to know what variables make the most accurate predictions concerning the DBA, what factors are the best predictors of succeeding in our psych program or in our treatment program. You want to find the best combination of intake variables that best predicts whether a patient will succeed in treatment, for example. Also explanation, you want to make causal inferences when you have a non-experimental design or some sort of flawed experimental design, and you want to control for a bunch of confounders, and then see, is there, after I control for these confounders, is there a relationship between my IV of interest and the DB? Because you can't randomly assign, for example, clients to 2 types of treatment, you collect information at intake about their level of distress, prior mental health history, counselor assigned age, the counselor they got, their age, their drugs, etc. Oops, lost column. And you want to use those covariates when you analyze the relationship between successful job placement, that's your DV, yes, no, and the type of treatment they received, which is your IV of interest. So we're going to adjust for who they got, how old they are, their drug and alcohol use, and we're going to use those as covariates first to how they're associated with job placement, and then we're going to see, after we adjust for them, how well the actual type of treatment they received predicts it after adjusting for those factors. So in terms of sample size, in case you want to do one of these for your dissertations, a little rule of thumb from Peduzzi et al. Is that each level of a dependent variable has at least 10 outcomes of events of interest for each predictor or covariate in the model. So if you're studying tests or crashes, for example, you need to have 10 crashes for each predictor or covariate in the model, including dummies. So if you have a 2-level IV and a 2-level CV, then you need at least 2 times 10 or 20 participants for your study in the DV level of most interest, crash, dead, etc. So like chi-square, if you have categorical predictor variables, there need to be observations that populate all categories of the variable, so you can't have empty categories or categories less than 5. Remember, maybe you don't, but that sort of weirdness. So, you know, basically, a rule of thumb is I need 10 participants per category or per level of independent variable is a sort of good way of looking at it. All right, well, let's talk about assumptions of logistic regression. So independence of observation, that is, each person's only in your data set one time. It's not families or couples or whatever. There's no outliers among your predictors, both at the univariate or multivariate level. You have no multicollinearity or singularity, which basically means, if you remember back to linear regression, your predictors are not redundant. So multicollinearity is mostly redundant, and singularity is completely redundant. And the example is always, you can't use the IQ subscales and then the total IQ score together as predictors. You got to pick total score or subscales, or leave out some subscales, something like that, so that you don't have complete redundancy. So the final assumption is that you have measured things accurately and reliably, so you do not have measurement error. So note that the following are not assumptions. Normality of everything with everything. So normality is not an assumption. Linearity, it's not linear regression, right? So there is no assumption of linearity between every predictor and the DV. So there is this other one that is sort of like, if you have continuous predictors, there's an assumption that they are linear in the log odds, which if you need to test that one, just hit me up in email and help you with that in the future. But basically, things don't have to be linear. And because you can always categorize the variables, even if you have a violation of the linearity assumption, there's ways to get around it using dummy variables. And finally, there's no homoskedasticity assumption for logistic analysis. So hopefully, I mean, those top four are not hard. It's these bottom three that are the hard ones. So hopefully you realize this is pretty darn straightforward and easy. So remember building equations with linear regression? There was enter, and there was backwards, and there was stepwise. Same idea here. You can either force everything in and build your own equation, or have SPSS build different equations and you compare them. So the methods are similar to linear regression. There's enter, same. It just throws all your predictors in and estimates a single model and tells you how much variance they account for, and regardless of the significance of the predictors. So it is the method, it's actually the most common method, gotta be honest, because we're usually not interested in building the most efficient model. We're hypothesis testing, like we want to adjust for a bunch of stuff, whether it ends up being significant or not, and then we want to see if there's a relationship between the IV we care about and the DV. So here's a new one. It's called forward. So it's kind of the opposite of backwards, which is coming up. But forward enters variables one at a time, like a stepwise, picking the best predictor. And it says, okay, among their remaining predictors, is there still any that account for a significant amount of variability? Cool, put that one in. Next step, it'll add a third one if there's a third one. And it keeps going until none of the predictors that are not in the model no longer add to your ability to predict the DV. So how this differs from stepwise is it never takes stuff out. It only goes forward, hence the name. Backward is exactly like it was in linear regression. Throws everything in the kitchen sink method, all predictors go in, and then it takes out the junky ones, one at a time. And then there is something called sequential, which is another new one. Basically, you do the order of things. So you say, first adjust for these covariates. Cool, got your model. Now throw in my IV I care about. That'd be a sequential model. And so it's done for predictive testing. So how do you pick the best model? So just like linear regression, except you got one more thing here. So there are 4 criteria to choose the best model among several possibilities. And again, this is done if your goal is to find the best prediction model rather than for theory testing. So you've got R squared, just like in linear regression, but it's called Nagelkerke R squared because, I don't know, someone's dissertation and the person's name was Nagelkerke, probably. So basically, it's the same sort of thing. It's the proportion of variability in the DV accounted for by the combined predictors that are in the model. So better models have a higher proportion of variability explained, so it's the same deal as normal R squared. So parsimony again, models that account for the same or similar variance with fewer predictors might be a better model. So that's the same as linear regression as well. In general, fewer predictors without a large decrease in your Nagelkerke R squared is better. Again, we have practicality. So if there are certain predictors that are easier to obtain and you can get a good model with those easier to obtain or cheaper to obtain predictors, maybe that's a better model. So that's the same as linear regression. So what's the new one? The new one is something called classification table. So the classification table tells you how well the model categorizes the actual observations on the outcome variable. So you know for your DV whether someone was a 0 or a 1, whatever it happens to be, died, didn't die, etc. Passed, didn't pass. But what happens is the model predicts what category they're in, and you can see actual versus what the model predicts. And good models more closely match reality, so they do a better job of actually putting people who died in the died box and didn't die in the didn't die box, or crashed in the crash box and didn't crash in the didn't crash box. So it's a really practical way of saying this model is better because it correctly classifies 75% of participants rather than 60% of participants. So how about choosing your predictor variables? So how do you know what the better predictor variables? Remember we had beta and squared semi-partial correlation in linear regression. So it's the same thing here. What do I use to determine what are the more important predictors? So it is an odds ratio. The thing that you use is called an OR, or an odds ratio, and SPSS predicts it for each predictor variable. It is a measure of the importance for the overall model of each predictor, like the standardized regression or beta coefficient in linear regression. So independent variables or covariates that have larger odd ratios are more important for predicting the variable's odds, so therefore they're more important for the overall model. So what do you do in the case where you've got one of these nominal variables that has like a bunch of dummies? So like each one of those is going to have an odds ratio. So how do you know, like, overall the variable, if you're comparing overweight, underweight, and obese are three separate odds ratios, how do you kind of like average them out, or how do you know how important overall BMI was, for example? And it turns out there's an overall omnibus test. So at the top of the three dummy variables in the table that shows the logistic regression coefficients, there will be a row that shows an overall test that tells you if that particular variable is significant for predicting the outcome variable. So I'll show an example of that coming up. So this begs the question, what the heck are odds ratios? Which sound weird, right? So logistic regression, again, doesn't analyze the raw outcome, the 0, 1 variable. It converts it into something called log odds, or logit. And it's the log odds of being in the outcome group coded 1. So all that is the odds of being in the group coded 1 is what it tries to predict. And then it takes the log of it. So anyway, it's a weird sounding name, but it's not actually as complicated as it sounds. So the most common way of interpreting odds is not to look at the odds themselves, but to turn them into what are called odds ratios, which is what we're talking about here. So they tell you the change in odds of the DV for a 1 unit change in the independent variable. So back in linear regression, the B parameters told you the change in the Y variable for 1 unit change in the X variable. This tells you the change in odds of being in the group coded 1 for a 1 unit change in the independent variable. So an odds ratio is the odds of the outcome for a level divided by the odds of the outcome for the referent level. So how do you interpret these things? So if you get an odds ratio, or an OR, that's less than 1 and it's significant, it means that as the predictor increases, the odds of the outcome level coded 1 decrease. So the odds, if you're looking at successful program completion is coded 1, you got an odds ratio that's less than 1. It means that higher values on that predictor are associated with lower odds of finishing the program, lower odds of the outcome of interest. An odds ratio that's basically 1 or not significant tells you that this predictor is not significantly associated with change in the odds of being in the group coded 1 on the DV. So ORs of basically 1, up or down a couple extra red Skittles, usually they're not significant as well, tell you that this odds ratio is not really associated with change in the predictor, the odds of the outcome variable. So if you get an odds ratio that's greater than 1, It's like a positive correlation. As the predictor increases, the odds of the outcome increase. So the odds ratio, the very first one there, less than 1, is like a negative correlation if you think about it. As the predictor increases, odds of the outcome decrease. Odds ratios that are greater than 1, as the predictor increases, odds of the outcome also increase. So again, what are odds ratios? So Cookie Monster doesn't like it. So my experience is that even I can talk about them all I want and tell you that one's greater than 1, or associated with increased odds, and one's less than 1, or decreased odds, but it doesn't really help. So what I teach you to do is convert them to percentage change. So this typically makes more sense, and having done this for a living, I can tell you percentage change makes a heck of a lot more sense to bosses and dissertation chairs, etc. So there's a little formula you use to convert an odds ratio to percentage change. So if your odds ratio is less than 1 and significant, then you use this little 1 minus the odds ratio times 100 formula. That's it. 1 minus the OR times 100 gives you the change in odds decrease, because it's an odds ratio less than 1. So let's say you had an odd ratio of 0.59. If you do the little formula, 1 minus 0.59 times 100, you get a 41% decrease in the odds of the outcome group coded 1, basically. So for example, it'd be like a 41% decrease in odds of completing the program, or odds of getting in a crash, or odds of getting another DUI. But it's lower because the odds ratio is less than 1. If you have an odds ratio greater than 1, the formula is a little different, but not much. It's OR minus 1 instead of 1 minus OR times 100. And this gives you the percentage increase in the odds of the outcome group coded 1. So let's say you had an odds ratio of 1.68. Do your little formula, 1.68 minus 1 times 100, 68% increase in the odds of the outcome. So if 1 is crashing, it would be a 68% increase in crashing. If the DV variable coded 1 means completion of the program, it would be a 68% higher odds of completing the program. If it was dying from COVID, it would be a 68% higher odds of dying from COVID. So you're ready for a worked example? I know you are. We're going to do a couple of these just to get you familiar with it, because there's several new concepts in here. Do California drivers with licenses to drive commercial vehicles have higher odds of crashing in a 1-year period than those with a non-commercial license? So this is comparing first year of licensure folks who have commercial licenses to drive big rigs and buses and tank vehicles, things like that, to normal drivers. Do they have higher odds of crashing in that first year? So here's what the data look like. These are real data. It's a big old file. Got their hair color, sex, age, BMI, eye color, license class, crash, tickets, all the stuff in your license, except for the fact that I code yes or no, you got a ticket or got a crash. So under those words, you guys know that there are numbers, and you can see over in the crash and ticket columns, there's just zeros and ones. Only one person got a crash in that whole thing we're looking at. They're the 1, and it looks like it's line 5. So DV variables, here we're doing crash status, not ticket, okay? So crash status is coded, 0 is did not crash, and 1 is crashed. So we're going to predicting the odds of crashing in your first year, because it's the level coded 1. So there's crash. You can see there's only one person who crashed. Over there on the, when I turn off the labels, you can see that person's coded 1. All the no's are zeros. So the independent variable here is the type of license they have. Do they have a 0 non-commercial or a 1 commercial? So find the variable column there that is called license class. You can see everyone here is non-commercial. That's most licenses are, class C or normal cars or whatnot. See over on the right, they're all coded as 0. Non-commercial is coded as 0. So commercials would be coded as 1. So when we do this equation, we're going to be predicting the odds of a commercial driver crashing compared to a non-commercial driver. So first thing we're going to do is, before you get crazy and do logistic, let's just do a chi-square, right? Chi-square to see if type of license is independent of your odds of crash or your likelihood of crashing. So remember that's under descriptive and crosstabs. You probably don't, but there it is. So here we go. We have our cross tabulation here. You can see Among non-commercial drivers, that's the rows are non-commercial and commercial. The columns are crashed, no or yes. 6%, and these would be row percentages, not column percentages. Why? Because we don't have equal numbers of non-commercial and commercial drivers, so you have to do the row percent, because otherwise there's always going to be more non-commercial drivers and everything, because there's a hell of a lot more of them on the road. So row percent, it's the percent of non-commercial drivers who crashed, 6%. How about commercial drivers? 9.7%. So that's over a 50% increase, right? So 9.7 is, it appears to be higher than 6, right? Is it statistically significant? There's our chi-square. We look at that first row there, and our sig is less than 0.05, so yes. Because our sig is less than 0.05, we conclude that license class and having crashed are related to each other. And in fact, we can look at the standardized adjusted residuals, and we can see that it's negative for non-commercials, negative 5.4, and positive 5.4 for commercial. So remember, those are kind of like z-scores. They tell you like where things are higher or lower than expectation if they're 2 or bigger. Negative means lower, positive 2 or bigger means higher. So it tells you that those two, the crashed and non-crashed, this is a 2x2 table, so it kind of always works out that things like it's 5.4 for no crashing and then negative 5.4 for crashing for non-commercials. It just flips because it's a 2x2 table. They just sort of work like this. So you just pick a column, okay? So specifically, these results tell us 9.7% of commercial drivers crashed, versus only 6% of commercial drivers, and that's a statistically significant difference. So there is 3.7 percentage point higher commercial drivers crashing in their first year than non-commercial drivers. So they crash more. That's, God, that was a complicated way of saying that. Yes, they crash more, 50% more. So let's actually do the logistic regression. It's under Analyze Regression Binary Logistic. I've put crash in my dependent variable box. I put license class in my covariates box. So everything here is a covariate, whether it's an IV or a covariate. It's just they cannot seem to keep the same nomenclature. So anyway, now you know. So dependent, I put crash. All predictors here, including the IV, are called covariates. And so license class is our only predictor. So because license class is a nominal variable, right? It's either you got a non-commercial or a commercial license. We have to tell SPSS to create dummy variables for it. So we click this little categorical button and we tell SPSS to make dummy variables for it, and then which level is going to be the referent level. So let me show you what that looks like. So this is where you tell SPSS the dummy coding. I have moved license class from the left, where it was covariates, to categorical covariates on the right there. And you have to set the referent level. So it has a default, and I think default's last. But you set the referent level to the level that makes sense. So to me here, it makes sense that we would compare non-commercial drivers, or excuse me, commercial drivers to non-commercial drivers, right? They're sort of the special group, the big rig drivers. You want to know, do they crash more than normal drivers, right? So the referent here we've set as first. So if you think about how this variable is coded, first 0 was equal to non-commercial, which is lower, right? It's the first value, I guess. 1 was commercial. So by clicking first and clicking change, we're going to be comparing the higher value, that is commercial drivers, to non-commercial drivers. So the resulting odds ratio we get from this will tell us the change in crash odds associated with being a commercial driver, that's a 1, versus a non-commercial driver, a 0. That is the first value, like numerically 0, 1. So first is 0. And so they're going to be the referent, and that's the rest of us, non-commercial drivers with their normal licenses. So make sure to click change. All right, so SPSS tells you how all your variables are coded, and this becomes really important because you forget this stuff. So you get this dependent variable encoding, and that's where you see how the dependent variable is coded. And remember, that's crash. 0 is no, 1 is yes. So we're going to predicting, remember, logistic predicts the odds of being in the DV level that's coded as 1, so that's going to be people who crashed. So we're predicting the odds of crashing. Down in categorical variables coding, the dummy variable represents the group that's coded as 1 versus the group coded as 0 across all dummy variables. There's only one dummy variable. So here, a 1 on the dummy variable means you're a commercial driver, right? So the odds ratio we get for license class is going to tell us the odds of a commercial driver crashing compared to a non-commercial driver. So the change, the difference. So it's really important to look here. This is how you kind of know how to interpret your results, is by looking at this table and going, okay, which one's coded 1 for each of my predictors? That's how you know which variable is, or how to interpret the odds ratio you get. So when you do the output, you get this thing called block 0, which is just awful that it does this to you. Never look at block 0. So I'm telling you here, cross out and ignore block 0. It's on the output. It's confusing. It's a model with no predictors in it that it just kind of does to be annoying because SPSS hates us. So ignore everything under the block 0 header. We want block 1. So block 1 includes our predictor. So here we go. Block 1, we've got a model. In this first one called omnibus test of model coefficients, you get a chi-square test here. And remember the F test or the ANOVA test from linear regression that kind of told you overall, does this model significantly predict the DV? This is the same thing, but it's a chi-square. Overall, does this model with one predictor in it, the license class, significantly predict your odds of crashing? If the sig is less than 0.05, then yeah, it does, just like that ANOVA in linear regression. So because the sig here is less than 0.05, it means that yes, this model we just made at block 1, which includes license class, significantly predicts your odds of crashing. So this next table, model summary, we get our Nagle-Kirky R squared. And so our Nagle-Kirky R squared is 0.002. It's really small. So turn that into a percent by scooting the decimal over twice. So our model predicts 0.2% of odds of crashing. So not much at all. That means 98.8% of why people crash, yeah, not predicted by this model. So we don't know why they crash. So why is that significant if it's so darn small? Look at the sample size. The sample size for this is, what, 34,000 plus 2,000? It's like 36,000 people. It's a big, big file. Okay, this is, you have a lot of power here to detect little tiny findings, because the sample size is so huge. So finally, down here in this variables in the equation table, you get your actual odds ratio. So being SPSS, it doesn't call it odds ratio, it calls it EXPB. Again, because they hate us. So that is our odds ratio. And on the row for license class, you also have a constant like you did with linear regression. It's not super interesting, just like it wasn't with linear regression. So I'm not going to focus on it, but the license class odds ratio is interesting. So note, there it is, 1.689, and it's statistically significant, and it's greater than 1. So remember, what's represented by license class? What group was coded 1 on that? That was commercial drivers. Commercial drivers have higher odds of crashing. In fact, if you turn it into a percent, so 1.689 minus 1 times 100 is about 69%. So the odds of commercial drivers crashing are 69% higher than those of non-commercial drivers in their first year of licensure. So they're a heck of a lot more likely to crash, right? That is the finding. So let's do a more complicated one. That's as simple as it gets. One predictor, 2 levels, that's really simple. So let's try to do a little more complex one. Let's do the BMI one. So remember, BMI has 4 levels. So is body mass index related to your chances of crashing in your first year of driving? So your dependent variable, again, is crashed. 0 is did not crash. 1 is you crashed again. And there's our variables in there, no and yes, so that's the same. BMI, however, has got several levels. There's 0 meant your normal weight, 1 was underweight, 2 was overweight, and 3 was obese. So there's BMI with the labels on. You can see the different BMI categories in there. And then on the right, you can see underlying those categories, those labels again, is numbers. So 3 is obese, 2 is overweight, and normal is coded as 0. So again, let's do a chi-square just to see, is BMI related to your crashing, whether people crashed or not during their first year of licensure? I went into crosstabs, busted it out. Here's what we get. So the columns again are no and yes crashed, and the rows are the BMIs. And notice now there's more rows than there was before, right? So 6.1% of the normal weight people crashed versus 6.3% of the overweight people. Doesn't seem like a big difference, right? Versus 6.1% of the overweight people. Okay, doesn't seem different. Versus 6% of the obese people. So are those little tiny differences between those percentages statistically significant? Well, let's go down to our chi-square. Chi-square sig is 0.962, not less than 0.05. So what would we conclude? Well, BMI does not appear to be related to your odds of crashing in your first year. Which makes sense, right? Why would it be? So about the same percentages of drivers crashed in their first year regardless of their BMI. Good, that makes sense. But let's go ahead and do the logistic regression anyway. So you can juxtapose chi-square, which you kind of understand, to what comes out of this logistic regression. Like, we wouldn't expect this thing to be statistically significant, right? Okay, so the dummy coding of BMI is also accomplished using the options under that categorical button. So I've just kind of skipped here. So I'm showing you BMI, and I've chosen first as the comparison group. What was the lowest numeric value for BMI? It was 0. And what was 0? Normal weight. So we're going to get dummy variables for overweight, underweight, overweight, and obese. And the odds ratios are going to tell us the odds of each of those categories crashing during their first year compared to normal weight drivers. So just make sure you change it to something meaningful. And I tell you in the homework assignment, like, what should be the referent category. And make sure you click change before you go to the next screen, or you'll be very sad. All right, so note that SPSS makes 3 dummy variables for BMI. It's K minus 1, number of categories minus 1. And so one category gets left out, and that's the referent, right? So here's our dependent variable. It's still 0 and 1. 1 was yes, you crashed. But look down at categorical variables codings. I love the bad grammar here. So BMI 1, dummy 1, that is the parentheses 1, represents underweight. How did I know that? Well, in that column, which group is coded as a 1 on dummy variable 1? Well, if you scooch over and look, it's underweight. All the other categories are 0. Dummy variable 2, what does it represent? Well, which category is coded as a 1? It's overweight, right? So dummy variable 2 represents the overweight folks. How about dummy variable 3? Dummy variable 3 is obese. Why? Because they're the group coded 1. So who's left out? Which group didn't get a dummy variable? There's 0 across all 3 dummy variables. That is your normal weight. So what that means is that each of these BMI levels, underweight, overweight, and obese, will be compared by its dummy to the referent level. The referent level here is normal weight because it's 0 across all the dummy variables. See? All right, let's do it. So we got I've skipped past Nagel-Kirky and all that stuff and just gone straight to variables in the equation. So the output line that says BMI, that doesn't have an odds ratio, see that top one up there, BMI? That is that overall omnibus test that tells you, is BMI related to your odds of crashing? So I told you for these excuse me, nominal dummy variables that have more than 2 levels, it gives you this overall sort of test that tells you if that predictor is significant, and that's it. And you can see it's 0.962 is the significance for BMI overall on that line. And again, it's one that doesn't have an EXPB. So indeed, this suggests because it's greater than 0.05 that BMI is not associated with your odds of crashing in your first year of driving. Cool. So note also that none of the sig values for the dummy odds ratios, that is BMI 1, BMI 2, and BMI 3, is significant. Those are also greater than 0.05. So cool. BMI does not appear to be related to your odds of crashing. That's consistent with the chi-square, so hopefully that makes some sense to you. All right. Oh, there we go. So I was just highlighting that it was sig. So do note that these odds ratios aren't exactly 1, right? Meaning no relationship. But what's going on is the sig are greater than 0.05, which tells you they're basically 1. Okay, for all intents and purposes, those are close enough to 1 to be 1. So no relationship between any of those levels and your odds of crashing. So let's do a slightly more complex example. Is your driver BMI related to your chances of getting a ticket during your first year of driving? It's the same analysis, but instead I've changed the DV here to ticket instead of crashed. So again, 0 is no, you didn't get a ticket your first year. 1 is yes, you did get a ticket. And here's that variables in the equation table. So let's first go to that omnibus test for BMI. Look at the sig value. It's less than 0.05. What? BMI is related to your odds of getting a ticket your first year of driving. Weird. Okay, so let's start looking at why, because the sig's less than 0.05. So let's go down and start looking at the individual odds ratios. Find the ones that are the dummy variables that are less than 0.05. So here's the first one. It's underweight. Sig is 0.967. Is being underweight different from normal weight in terms of odds of getting a ticket? No. Why? Sig is way greater than 0.05. Okay, how about the next one? Next one is overweight. Overweight, the sig is 000, so that's definitely less than 0.05. So overweight people had different odds of getting a ticket from normal weight people. Normal weight is the referent again. What is that difference in odds? Well, look at the EXPB. It's 1.143. It's greater than 1, so they had higher odds of getting a ticket. If you do that little formula, 1.141 minus 1 times 100, you get about 14.3%. So overweight folks, sig was less than 0.05, they have 14.3% higher odds of being ticketed during their first year of driving than normal weight drivers. Why? I don't know why overweight people have a higher odds of crashing, or getting a ticket. All right, how about the third group? That's obese, sig's less than 0.05. Odds ratio is 1.118, so again, higher odds of getting a ticket if you're obese. So if we use a little formula to turn that into percentage change, it's 1.118 minus 1 times 100. They have 11.8% higher odds of getting a ticket their first year if you're obese than if you're normal weight BMI. I don't know why. Yeah, exactly. Huh? So how does that make sense? Why would being overweight or obese have higher odds of getting tickets than normal weight drivers? It really is kind of like mind-bogglingly weird, right? So could this just be the usual confounding by things like age or sex? You know, maybe there's, I mean, who knows, right? Maybe males tend to get more tickets, so maybe they tend to have higher BMI or something like that. Or older people tend to have lower BMI and older people don't get tickets, something like that. Who knows? So we're going to repeat that prior analysis, but we're going to add age and sex as possible confounders. So we're going to adjust for them and then see, is your license class still associated with your odds of being ticketed during your first year? And you just throw them in the model to do this. So the way it's coded is sex is coded here, 0 is female, 1 is male. Age is just continuous years of age. Like we don't need to make dummy variables for it. It's how old you were when you got your license. Were you 17, 18, 19, 20, 20, etc. All right, so the first stop here, I've thrown them in the model, is to look at the categoricals, variables, codings table. And note it's a little more complicated now. You've got BMI in here. So BMI is coded the same. Dummy variable 1 is underweight. It's got a 1 there. Dummy variable 2 is overweight. and dummy variable 3 is obese. But what's going on below there? Well, sex is also in the model now. We've told SPSS that it is also categorical. So we had to set up which one we want to be the reference for that. Which group is coded 1? Male. So the dummy variable for sex represents males compared to females. All right, so it's going to be the odds of a male getting a ticket versus the odds of a female getting a ticket during their first year. The sex dummy variable, yep, that's what I just said. So note that age doesn't have dummy variables. Okay, don't make dummy variables for continuous variables. You don't need them. Okay, it's you just throw them in the model and let it go. Okay. So what does the odds ratio then for age mean? Well, it indicates the change in the odds of being ticketed for each 1 year increase in your age at licensure. So what's the change in your odds of getting a ticket for every one year older you are when you get a license? So let's try to interpret this. So there's our variables in the equation table. We got the BMI overall test again on that first line is the one without an EXPB, and SIG is less than 0.05. So even after we adjusted for age and sex differences, BMI is still associated with your odds of getting a ticket during your first year of licensure. So let's go down through the dummies for BMI and interpret them. For underweight, the SIG is greater than 0.05, so the odds of underweight people getting tickets were no different than those for normal weight people. Okay. How about obese and overweight? Both SIG, both 1.183, just kind of by chance worked out that way. So do the little formula, and they're both SIG. So do the little formula, 1.183 minus 1 times 100. Both overweight and obese drivers have 18.3% higher odds of being ticketed compared to normal weight drivers, even after adjusting for differences in age and sex. Really weird. Don't know why. So we do have some other variables in here. We've got sex, right? The sex dummy variable, statistically significant. The odds ratio is 1.696. Remember that represents males, right? From the categoricals, variables, codings. Males have 69.6% higher odds of being ticketed their first year of driving compared to females. That makes sense. How about the age one? So the age one, remember that was a continuous variable. We didn't make dummies for it. It's got an odds ratio of 0.971. What the heck? And it's significant, sorry. So what does 0.971 mean? Well, it's less than 1, right? It's an odds ratio less than 1. So it means that as the predictor goes up, your odds of being in the group coded 1 for the DV, that is getting a ticket, go down. So for every 1 year increase in age at licensure, your odds of getting a ticket, if you do the little formula, 1 minus 0.971 times 100, were 2.9% lower, so about 3% lower odds for every year older you were when you were licensed. And so what's kind of cool about that is, what if someone's 10 years older? Well, you can multiply the 2.9 times 10, they'd be 29% lower, okay? So continuous variables in logistic are really easy to interpret because you can do that kind of stuff. So anyway, that's your first odds ratio that's less than 1. And note that because it's significant and the odds ratio is less than 1, it means for every year older, that is a 1 unit change in the predictor, the odds of the outcome are lower. So they're 2.9% lower specifically. So finally, there is a logistic regression summary table in the APA write-up. Make sure you note it. So you got to take all that stuff from above and turn it into this table down below. You got beta, something called SEB. That's standard error. It's the SE in the table up top from SPSS. You got your odds ratio. What else? You star the betas that have a SIG that's less than 0.05. Note the stars. Your betas go there. Excuse me, your B's go there. Your standard error of betas go there. Note the ones with a line for those. And then they have an odds ratio of 1. That's the referent group. That's how you tell your readers who the referent group. Normal was the referent group for BMI. Female was the referent group for sex. And there is no reference group for age because we didn't categorically code it, right? So your odds ratios come from the EXPB column. You round them to 2 decimals. And one other thing is there is a sentence in your write-up where you talk about overall, this model significantly predicted odds of crashing or odds of getting a ticket, right? So I'm just showing you that comes from this table called Omnibus Tests of Model Coefficients. Use the row titled Model. There's your Nagel-Kirk R-squared. So this model that's got age, sex, and BMI accounts for scooch to decimal over 5.6% of the variability. And this is how you would write this sucker up. So a chi-square of 5 n equals 36,655 is equal to a chi-square value of 1200.57. P was less than 0.05, and Nagel-Kirk R-squared to 2 decimals is 0.06. 0.056 rounds to 0.06. All right, good luck on this, and hit me up in the discussion if you have any questions.